Hey guys, what is up? Today we'll be discussing the Lead Code Sunday contest, 461. Let's get started with the solutions. Yes, I was able to finish all the four problems, and I think pretty much got a decent rank of 669. And yeah, so let's get started with the problems. Um, So the first problem was pretty straightforward. So it says that we want to find a trionic array. So trionic array is basically, let's say, let me go down, and yeah. So basically, you want to find index p and q such that this guy is strictly increasing, this is strictly decreasing, and this is strictly increasing again. So this problem you can like solve it in O of n time complexity, because we can just notice that for every p there can only be one q, right? So if you have a p and you're going on a decreasing path, it cannot happen that it will suddenly start increasing from here, and then it will also starting, like, it cannot go two ways, right? From this index it can go only in one direction. It can either increase, decrease, or it can be equal, right? So so that's why if it's decreasing, then it will decrease up to some point, and then it will start to increase, right? So this statement basically holds for every p there can only be one q, right? So that's what I think we have to do here. Like we just have to, like, just check if the array is trionic or not, right? So this part is easy, like you just start from 0 and you end at n minus 1, right? So that's what I'm checking. So I just start from 0 and I just want to find a p, right? So I'm just comparing if it's strictly increasing, right? And then for q I start from the back, right? So I just start from the back and I check if it's decreasing from here, right? So that's how I find q, and then I check what's in between p and q, right? So if in between p and q, is it like strictly decreasing or not? That's the check over here. And then yeah, just some logic, that's it. So yeah, moving on to the second problem. uh yeah, maximum balance shipments. Okay, so this one was a little bit tricky to think, but I mean, the code was really simple, but to prove the code is working, it was kind of it took me 5 or 10 minutes to come up with that. So I'll just discuss what I thought here. And so basically the problem states that so the problem states that you are given an array of weights, let's say 2, 5, 1, 4, 3, and let's say you pick some non-overlapping sub-arrays like this. So the maximum here is 5, which is greater than the last element. The maximum here is 4, which is again greater than the last element. So what's the maximum number of sub-arrays you can make such that this particular condition of max being greater than the last element of a subarray holds, right? That's the problem. So again, this one was also like you can again solve it using this line graph approach. Like for example, any array, like any random array, can always be represented by a line graph. Like you can have peaks and valleys, right? So for example, if let's say your subarray looks like this, I mean your array looks like this, right? This is 0, this is n minus 1, okay? The indexes, I mean. So if it's like strictly increasing, then you have to keep going forward. You cannot have the last element to be like less than the maximum. So for example, if you're standing over here, then the last element is itself the maximum, right? So you cannot have that. So what you have to do is you need to find at least one decreasing part. So let's say this is the next element with decreases. So you basically choose this subarray greedily, right? Because we want to maximize the number of subarrays, right? So you basically choose that subarray, and then you start from the next index, right here. So let's say this is index I, this is index I plus 1. And now we are on a decreasing part, right? So decreasing part, again, you can choose this particular array greedily, right? Because let's say the subarray looks like this, 10 and 8. So you can just choose this one because 10 is the maximum, which is greater than 8, right? So our hypothesis, I mean our statement here is, if we are on the increasing path, we choose a hook like a array which looks like a hook like this. It should have at least one decreasing. And if we are on decreasing path, then we choose two elements, right? The first element and the second one, right? And again, repeat the same process. Like decreasing path, just keep choosing it greedily. Increasing path, keep choosing greedily. So for example, for here, you'll choose something like this till here, then this, all of these you'll choose, and yeah, you keep choosing like that. Okay, so this will basically maximize your number of subarrays. So yeah, I'll just demonstrate this example in this one. 2, 5, 1, 4, 3, right? So 2 is I'll just make a graph. 2, and then you have 5, and then 1. I'll just slide all the numbers, 1, 2, 3, 4, 5. So 2, then you have 5, then you got 1, then you got 4, then you got 3. Alright, so your graph looks like this. I mean, your array looks like this, right? So you choose this, and this, right? Because you need at least one increasing element in this increasing array. So this is your one array, and the second one is this one, right? As we discussed, like two elements in the decreasing part. So the answer is 2. Yep. So that's what you have to do. That's what you have to do. Like just have the you can just do that using by keeping track of the maximum element. That's the maximum element is the first element, and as soon as you find I which is decreasing from the running max, you just increment the count. So this is basically checking this condition, this hook shape array, right? And else you just keep the track of the running maximum. Yeah. And this will, this if will also cover this condition, right? So if it's decreasing, then the maximum, your double weight of I will obviously be less than the maximum, right? So it will also check for this condition. It will basically you're killing two birds with one stone. So both of this will be covered. Yeah. So let's move on to this third problem. Minimum time to activate string. Okay, this one was again a bit tricky to think, but it was pretty simple. If you see the solution, it's really short. So what you have to do is you are given some strings, one string. So let's say you're given a string cat, and you're also given order of operations 0, 2, 1, for example, which is a permutation of numbers from the range 0 to n minus 1. N is the length of the string. Okay, so first is 0. So at this is time 1, time 2, time 3. So at time 0, you'll put position 0, you'll replace position 0 with an asterisk. So now your string becomes like this *80. Okay, so how many strings contain an asterisk in this? So there are literally only 3 strings: star, star A, star AT, right? So that's what number of strings contain asterisk are I think they are called active strings, right? So here the active count is 3. Now we replace 2, the position 2, which is this T, with an asterisk. So now your string will look like this: star A, star A. Star A, star. So how many strings contain asterisk? So they would be the above strings plus the new ones, right? So new ones, they're only these two. You have just a star and a star. The above ones are these 3. But you may argue that star AT, this is an old string which contains a T, but we replace it with the asterisk. So yeah, you don't have to actually count it because it is already counted. So that's why your above case is already covered, right? So it doesn't matter if you say it's a star AT or it's a star A star. All that it matters that it is counted once, right? So that's why that's a most critical observation of this problem, by the way. So the active count is 5 again, right? And then I'll just replace this one with also a star. So again, above plus new. So above is like there are 5 strings and the new ones. So how many new ones are there? Only this guy is new, right? Because all of these are covered, right? Because it has asterisk to the adjacent one. So new one is there's only one string which is new. So which is 3 plus 5 plus 1, which is 9, right? So as soon as you hit not the prefix sum, but 5 plus 1, which is 6, right? So above plus new, above is 5 plus 1, 6, yeah. And k is given 6, so as soon as you hit k, you just have to return at what time 0, 1, 2, you basically passed an active count of return equal to k, right? So the intuition, I will just explain this problem from another angle. So let's say this is a star, you're putting a star at time t, right? And then you have an adjacent star over here and an adjacent star over here. In between these you have all letters, okay? So you can be rest assured that when you put a star after these stars will already cover all the strings which will be like concerned with this particular star, right? So for example, let's say you might be concerned that hey, if we just put this particular star over here, then should we also consider the strings that go beyond the like the nearest star? Like let's say, do you want to consider this string? The answer is no, we don't want it, because it's already considered by this particular star index, right? So it will just say, so before there was a letter, let's say x over here, so this star will just say, okay, I will just take this x, right? I just want to count it. I don't care what's placed over here, right? As long as it's not a star. So that's why this particular string is already counted. It's already counted. As we saw in the above example, right? The star 80 example, where this one is already counted. Star 80, so star A star will already be counted. You don't just worry about the number, right? So that's the intuition. So basically now the problem reduces to how many strings lie beyond this. So let's say this is an index n, this is index x, this is index y, right? So you can have this, right? The number of strings over here is y minus n, number of strings over here is n minus x. Just multiply these two. So that will be the number of new strings, okay? And this you will add to the previous, which was the above, the above variable that we were talking about. Okay, so that's the code. You can just maintain a set of put order to find the adjacent asterisks, okay? And you can just do a binary search and just do whatever equation I told you guys to do, and just check if it's greater than or equal to k, and just return the answer. If it's not possible, return -1. That's pretty much it. Let's move on to the last problem. So the last problem is also it's a really good problem. It's like a really basic problem, but it was fun to solve. So you basically given again, it's a continuation of the first problem kind of, but it's an extension of the first problem, I would say. So let's say you are given LPQR, and let's say this is a trionic array, right? The trionic meaning LPQR. So L, P, Q, and R, right? This is R. So you have to find maximum sum of a trionic subarray. So there can be multiple trionic arrays inside the given array. That's the problem. Yeah, this is the problem. How do you do this? Yep. So again, we'll just start very simple. The first observation is that if there is an L, then if it's increasing, you have to find a local maxima, right? This is a local maxima. Fast. You have to do it really fast, right? Fast meaning you have to do it in O of n for all indices. So for L, let's say this is the local maxima beyond which we'll start dropping, right? So we'll drop, and let's say we reach till Q, And let's say for Q, this is the global, like the local maxima R, from which we start dropping. Okay, so let's say we have the ability to calculate this in O of n, and notice we also want to calculate a local minima for all indices, right? So second observation is that we have to calculate a local minima again in O of n, like really fast for all indices. Okay, so let's say this is P, and you start dropping till Q, right? And then you start increasing, and then you again start dropping, and you again start increasing, again start dropping, right? So this can be like example, right? So how do you do this? So for example, if so, a third observation is that if there exists a local maxima for an index exists, then its local minima would not exist, right? Because maxima exist for it. There can only be one guy which exists, and vice versa. Okay, yeah. So how do you do this fast? So if you can do this fast, the problem is solved. I mean, that was the problem. That's it. So how do you do it fast? So what you can do is like you can just keep a track of the running maximum. I mean, that's all you have to do here. Like, let's say your array looks like this: 0, -2, -1. Let's copy, I think, this one. Yeah, array looks like this. Okay, I think I blew up the -1 at the end. Yeah, so you got 0, you got -2. Okay, so you'll just calculate the inc table. Inc is the local maxima and dec is the local minima. Okay, so now for this guy, the increasing is like there's no increasing, it's just decreasing. So for 0 it will be -1, right? For -2, so 0, 1, 2, 3, 4, 5, 6. So for -2, again you are like dropping. You go to -1, and then you start again, go to like -2, so -1, right? And then you drop again, like it's like this: -2, -1, -3. So for -2, your index would be 2, right? So up till here only it increased. And then for -1, did we increase? No, it's decreasing. So again, there is no local maxima, so put it -1. So for -3, are we increasing? Yeah, for -3 we went to 0, 0 said we went to 2, and then from 2 we went to -1. So for -3, the index would be 5. For 0, the index would be 5 again. And for 2, are we increasing from 2? No, we are not. So index would be -1 again. And lastly for -1, there's no, the array is the standard. So for last element, it will always be -1. We are not doing anything, right? Yeah, so this is your increasing table. This you can calculate it in O of n, right? By doing some simple prefix the maxima, keeping a track of the maxima. And as soon as you see a break, like as soon as you see a drop, just update till the previous index, right? You don't need to update till the last index, like the whole array. And then you update the previous index to point to the next index, right? That's how you can calculate this in O of n. And then the dec table would look like, for 0 we went to -2, and from -2 we went to -1, right? So for this index, your decreasing is still 1, so you put index 1, right? Because we are just decreasing till here. Then for this guy, we went to -1, which is increasing. So basically, if it's increasing, just blindly you can put -1. So if this is increasing, there's no decreasing, right? And for these guys, there might exist a dec. So for -1, we will check again. So -1, we went to -3, which is below, right? For -3, we went to 0, which went to 2, and which went to -1. So -1 is like just the adjacent. So you just put 3, right? Index 3 basically with this guy. This is your local minima, index of the local minima. Then for 2, you went to -1, right? So you just put the last index, 6. So put 6 over here, okay? And for -1, you like didn't do anything. You didn't go up, you didn't go, like you don't even travel equally, like there's no -1, or they didn't go down because it's the last element, so it's again -1. So for the last element, both of the local maximum minimum will be -1, but for the other elements there might be, yeah, there might exist local maximas and minimas, right? So if it's a flat array, then everyone will be like -1, I think. -1 line of -1s, right? So what did we achieve using this? So we achieved a lot. We actually achieved an answer. So now it's real easy. You iterate over all the indices for I equals to 0 dot 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 till n-1, and your I will behave like an L, like your I is over here. So I के लिए, like, you can find the you have I, right? Then your P would be inc table, inc of I, right? So inc of I, just put the index I and you check inc of I is some, so you'll get some value. Then your Q would be inc of, so decrement of P, right? And your J would again be increment of Q. Again, there can be exist -1, so P can be -1 and Q can also be -1, right? So that's fine. You just can eliminate that condition. I mean, if that condition occurs, you can always disregard that answer. I mean, you can just move on to the next index. That's fine. That's just an handling of the condition using if else. But this is the idea. So again, one more. So now what you can do is, like, you can just maintain prefix sums. So P of like P minus P of I -1 plus P of Q minus P of P plus value V. I'll talk about value V. So plus some value, plus, sorry, P of J minus P of Q, right? So notice that this one is this part, I to P, this one is this part, this is excluded, and yeah, this is like Q, right? This is included. Here both of these are included. And this one is like, again, this part, Q to J, this one is included, this one is excluded, right? Because we counted in previous. So notice that this guy, you don't have any flexibility. This is fixed. This is also fixed. But this is flexible. Now, this is flexible because you have control on how much you want to increase. Do you want to increase till here? Do you want to increase till here? Do you want to increase till here? How much do you want to increase? But on these ones, you don't have that flexibility. You have to go till P. You have no other choice. You can't go till here and then say, okay, I'll decrease from here, because it is already increasing, right? Because it's fixed. The nature of the array is fixed. And similarly, it's fixed over here. You cannot go till here and say, okay, I want to increase from here, because it's still going down. That's why. But from here, you have the flexibility to choose. You can go till here, here, or here. So how do you choose, right? So notice, if like it's a highly negative array, so I'll just go back to my example that I got a wrong answer in the contest, by the way. So yeah, so let's say the number is -741, this is -635, this is -569, right? So either you can choose two elements, because obviously your J should be greater than Q. This is your J, this is your Q, right? Or you can choose all the way till above, like, okay? So you got two choices. Either choose two elements or choose all the elements, right? Because the benefit of choosing like all the elements is that you can also have the case that it increases till, like, let's say very large number, like plus infinity, right? Very large. So it's beneficial to choose this entire subarray. Or you can just minimize the cost, just choose two elements and not worry about the, like, going till the third element, right? Because let's say your number is like 10, -10, -8, -7. So some of these two is -18, some of these two is -25. So it's, if you see, it's like not in our benefit to choose it, because -25 is less than -18, right? And since we would at least choose two elements because of this condition of the index, we'll just choose two of them and be done with it. So you have two choices over here, and you take the maximum of both of these choices. Okay, so yeah, that's what you have to do. So here you just put one condition, p of q plus 1 minus p of q, okay, and take the maximum of these two. So yeah, that's pretty much it. That's the code here. I'm just calculating normal prefix sum, calculating the increasing table, right, and the decreasing table, right. So pretty straightforward. If you find an element that is increasing, just stop and you update the previous elements with that particular index, right. So for example, let's say guy is increasing and now it start to decrease. So for this guy, the local maxima is this index. For this guy, it's also this index. For this guy, it's also this index. For this guy, it's also this index, and so on. And if it's decreasing and increasing from here, so for this guy, and for this particular maxima, there is no increment, right? So it will be -1 because it's already in the maxima. But for this guy, let's say its decreasing index is this. For this guy, it's again this. For this guy, it's again this, right? For this, but for the valley, it's not anything, like it's -1 because we have increasing, right? So that's what this inner loop does in O of n. So total number of operations is O of n because you'll just like go back and go forth. It's actually O of 2n, right? Because yeah, you're just like moving in the forward direction again, just to update it with like do this stuff. Just put like how the index is populated in the tables. And yeah, basically just fix your I is your L, get the P, get the Q. So Q is deck table, J is a ink table. Have these two conditions here in the S3 and just update return the answer. So yeah, that's it. Hope you guys got the solutions. If you have any doubts, please feel free to comment. And thank you for watching. Please like, share, and subscribe. And yeah, that's it. Have a good Sunday.